Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Nabil Aiman and this is our first assignment for Bmmh 3553 heat transfer, where we'll do the assignment conduction graphical analysis on heat transfer. So my name is Nabil Aiman bin ALIAS and this is my group member Muhammad IZZUDDIN bin MOKHTAR, UMARUL HAKIMI bin HARUN, KAARTIK anak lelaki BALU and PARANY anak lelaki SURENDRAN. So this is our content layout for this assignment. So we present about the introduction, design simulation, analysis of the heat sink, discussion, and the last one is conclusion. So where did the heat sink used? They are most commonly used in computer but are also found in cell phone, DVD players, and even refrigerator. In computer, a heat sink is an attachment for a chip that prevent the chip from overheating, and in modern computer, it is as important as any other component. So what is the purpose of the heatsink? The purpose of the heatsink is to keep the component safe from overheating. Heatsink keep the temperature of the device at the desired range and prevent the accumulation of energy by absorbing it. So how did the heat sinks work? The heat sinks work by using a thermal conductor to take heat away from a heat source, drawing it toward its own large surface area that make contact with the cooling medium such as air or another fluid. The need for a large surface area is why the heat sink typically consists of a base connected to a number of very narrow fins or pins. This form is the best way of fitting as much surface area as possible into a given volume. That's all from me. I will pass to the next presenter for the selection design. Thank you.
Hi, Assalamualaikum. My name is HAKIMI bin Harun. My matrix number is P0919104555, and I will be presenting to you about the selection design. We conduct two selection design with two different material. For the first design, we are using copper material types. At the top view, the dimension of width and length is 40 mm times 40 mm. For the front view, the height of the design is 20 mm with the dimension between the fins is 2 mm and 4 mm at the middle of heatsink surface. The last one, right view, where the height from the base to the fin is 6 mm with 1 mm chamfer. Uh, and this is the isometric view for the selection design 1. For the second selection design is using alloy aluminium material type. At the top view, the dimension of width and length is 40 mm times 40 mm, same with the selection design 1. And we design a square hole with a dimension 8 mm times 8 mm at the center of the heatsink. The gap between each fin is 1 mm. For the front view, the height from the base to the bottom heat fin is 5 mm, and the height from the top of the heat sink to the bottom fins is 15 mm, which approximately 20 mm height. Lastly, this is the isometric view for the selection design 2. That's all from me. I will pass to the next presenter.
Hi, Assalamualaikum. My name is Muhammad IZZUDDIN bin MOKHTAR. I will continue about analysis. Okay, so this is guidance for simulation characteristic. The first one is ambient temperature. We put 30 degrees Celsius. Next one is film base size, 40 millimeter times by 40 millimeter. Next one, convection coefficient. We put 5.03 watt per meter square Kelvin. The next one, average heat flux on full size, we put 1,500 watts per meter square. Next one, average temperature on cold side is 76.6 degrees Celsius. The lastly, average temperature on the hot side, we put 37.3 degrees Celsius. Okay, after we analysis the thermal loads for design 1, on the hot sides, on the hot side temperature, we got 60, 65.1 degrees Celsius. On cold sides, we got 65 degrees Celsius. For design 2, the hot sides, we got 47.6 Celsius, and cold sides, we got 47.4 degrees Celsius. So I will continue about thermal loads. For design 1, convection for design 1 is entities 41 phase, convection coefficient 5.03 watt per meter square times Kelvin. But ambient temperature, we put 303 Kelvin. For the heat flux, entities 1 phase, heat flux value, we put 1500 watt per meter square. For design 2, heat flux, entities 1 phase, heat flux value, we put 1500 watt per meter square. For the convection, design 2, entities 314 phase, convection coefficient 5.03 watt per meter square times Kelvin. But ambient temperature, we put 303 Kelvin. That's all from me. I will pass to another member. Thank you.
Hi, my name is KAARTIK. Today I would like to discuss about our studies based on heat transfer. So we choose two material, which is copper and alloy. So these are the comparison of both material. First of all, the copper has a thermal conductivity of 390 watts, specific heat capacity of 390 joule, and its density 8,900 kilogram per meter cube, and its volume are 2 power of -5 meter cube, and its mass is 0.178 kilogram. While the alloy steel have 50 watts, specific capacity of 460 joule, density of 7,700 kilogram over meter cube, and volume of 2.0496 power of -5 meter cube, and its mass is 0.157 kilogram. So as you can see here of the first picture, you can see the copper's thermal conductivity, and the second picture of alloy steel's copper conductivity. What is thermal conduction is about? Thermal conduction defined as the transport of energy due to random molecular motion across a temperature gradient. So here, the copper have high thermal conductivity than alloy steel. It is used when there is a high level of thermal conduction is necessary due to its thermal conductivity. Here we can see the definition of thermal conductivity is well explained. The copper has high capacity to absorb and release the heat compared to the alloy steel. So here the alloy steel is much poorer compared to copper. Thank you.
Hi, my name is PARANY SURENDRAN. My metric number is B0919101212. I'm going to conclude this slide that we're going to choose the design. Second design is the perfect design because the length and the number of fins have increased and the temperature range has shrunk. Secondly, the copper is widely utilized in operating systems that demand a large quantity of thermal dissipation. And finally, because of its highly melting point and modest corrosion rate, copper has the highest thermal conductivity. It's also a good metal for reducing energy loss during the heat transmission. And this is the sample image of the second design. And that's all from us. Thank you so much.